Hello, everybody, and welcome to this IMechE Tribology webinar series. Today's talk is going to be about modeling cartilage rehydration, a numerical approach. But just before we get on to that and introduce our speaker for today, I just want to point out some of the housekeeping rules. This presentation is recorded, and so a copy will be sent out to everybody after the session. On the bottom of your screen, you'll be able to see a button that says CC, and this will enable you to have live captions added over the talk today. If you have any questions for our speaker, there is a question and answer box, so don't put your questions in the chat, put it into the Q&A box directly, and we'll be able to pose those to Arshad to answer. If there are any questions that we don't get to answer within the time limit for today, we'll always send those over so that they can be answered afterwards. The chat function, please make sure if you want to add any comments that it is set to everyone rather than just to an individual speaker, otherwise it'll only go to them directly. So with that, I'd like to introduce our speaker. Today we have Arshad Ashik joining us from Imperial College London. Arshad is a President's PhD scholar at Imperial College. He is working to develop a cartilage model that considers both the mechanical and tribological aspects of real cartilage. The model in future is expected to aid the development of biomaterials for cartilage and soft tissues. Prior to Imperial College London, Arshad worked with the US agricultural equipment manufacturer John Deere for a period of 3 years where he worked as a product engineer. There, he performed finite element analysis to virtually validate the crop care products before production. And during his studies at the Indian Institute of Technology in Delhi, he investigated 2 epoxy composites that could potentially replace the present ultra-high molecular weight polyethylene acetabular cups for hip implants. Some of Arshad's notable achievements include winning the Best Project Award for developing a smart stick for the visually impaired, securing the competitive presidential scholarship for his PhD studies at Imperial College London, and most recently, being awarded a second prize for the best oral presentation at the STLE UK conference, which was just last week. So I'll hand over to you, Arshad. Thank you very much for joining us today.
Thank you so much, Sarah, for the introduction. And thank you, IMechE, for giving me an opportunity to present at this forum. Good morning, everybody. My name is Cartilage. I'm a third-year PhD student at Imperial College London. I work with Professor Daniel Idini and Professor Kamini Putignano, and today I'm going to talk about cartilage modeling. If you look at, let's talk about cartilage first. Cartilage is a soft tissue that's present in your bone joints. It covers your bone surface, and the main functions of the cartilage are to distribute the load evenly to the bone surface, to lubricate the joint, and to separate the joints and to separate the bones from coming in direct contact. Now, if a cartilage is degenerated, you're going to end up in a case something like this. After the degeneration, the bones will come into direct contact, and that's when you'll start to experience excruciating pain. And this is something which we don't want to get into. And today, by the end of this presentation, I'll be able to give you some tips so that you'll be able to maintain a very healthy cartilage. To visualize a cartilage, it's best way to visualize it as a porous solid filled with interstitial solid, something like this. So this is an image from ChatGPT. I tried to make a very beautiful picture of cartilage that's filled with interstitial fluid, but I couldn't make something fancy as this. But this represents how a cartilage would look like. You have a porous solid, and then there's fluid filled inside the cartilage. With this information, let's try to understand how a bone joint works. So here we have a schematic of a knee joint. Here you can see the bones where the loads would come through. And then we have the cartilage that covers the bone surface. And this entire system is covered in a synovial bath. Now, what happens here is when you walk or when you involve in activities, these joints would oscillate against each other, and then there will be this synovial fluid that will go into the cartilage, and there will be synovial fluid also coming out of the cartilage. The best analogy of a cartilage is a sponge filled with water. So if you squeeze a sponge that's filled with water, there will be water coming out. And if you put the sponge in water, there will be like water absorbed within the sponge. This is a small FEM model that represents how a cartilage would work. So here, if you see, if there's a load that's applied to the cartilage, this is the velocity profile that you see at the end, where the fluid would just come out. And if you release the load, the cartilage would go back. And here you can see how the fluid would just go back into the cartilage. The information that's represented here on the top right corner, this is a bit of additional information. Now, what it means is this, here you have a SEM image of cartilage. Now, you have to imagine that cartilage itself is like a 2 mm thick material. Now, even in this 2 mm thick material, there's a lot of strength variations happening. So in this image, SEM image, if you see, on the top layer, so the top layer of the cartilage, it's a superficial zone. It's it doesn't have any strength at all. It's a very loosely packed region. But when you come to the middle of the cartilage, that's an area where we have more collagen fibers, and it has more strength compared to the top layer. And when it gets to the bottom where it's attached to the bone, it has strength very equivalent to that of the bone. Now, this bit of information, I'm not using this heterogeneous cartilage property, strength property for my modeling. But now, as we move forward, you'll be able to understand there are already a lot of complexities involved in cartilage modeling. So you'll be able to appreciate why I'm not using this particular heterogeneous cartilage strength in my model. All right, so before we proceed to the further slides, I'd like to ask you a very simple question. So here we have a very thin space. So just imagine this, the thickness of this is like in the range of micrometer. And if a fluid is supposed to flow in this particular region, the pressure that will be generated in this fluid will depend upon which fluid parameters. Will it be velocity? Will it be viscosity? The fluid geometry, just as you can see here, or all of the above? I'll give you 15 seconds to answer this poll, and after that, we'll move forward. Do we have the polls answered? For some reason, I can't see the poll results.
Can you see the
I
results
see.
now? Yeah.
Yeah, I can see the results now. All right. So I see most of y'all have answered 67%, all of the above. But if you answered velocity, that's right. If you answered viscosity, that's right. If you answered flow geometry, that's right. But for this particular context, the most appropriate answer is all of the above. Yeah. So moving with this information will be very necessary for us as we move forward to the modeling part. Now let's see this. So for cartilage modeling, we had two different components. So there's a fluid that's flowing outside the cartilage, and then we have cartilage as such. In this particular work, I'm considering the fluid outside the cartilage and cartilage as two different entities. And in this slide, we'll talk about the fluid that's flowing outside the cartilage. Now, this is very similar to the example that you saw before, in which a fluid is flowing through a very narrow, thin space. I mean, in this particular contact region, the space is very thin. It's in the range of micrometer, and the fluid has to pass through that particular space. In tribology, the most famous equation that's used to model the flow that's passing through thin space is Reynolds equation. So in the Reynolds equation, if you see, as you answered in the previous question, so H represents the film thickness or the geometry the flow will pass through. Eta is viscosity, and then we have the velocity of the flow. So as most of you all guessed it right. So the pressure distribution depends upon the flow geometry, viscosity, and then the velocity. In this particular case, for my modeling, I'm starting with a very simple case. I'm not dealing with the entire Reynolds equation. I just take the one-dimensional form by neglecting all the z-directional terms. So the equation would simplify to this particular form. And then what happens is, if I solve this differential equation, I can get the value of pressure for the fluid that's flowing in that particular thin space. And with that particular pressure information, I'll be able to extract the flow. Now, this is the point where we differ from the classical Reynolds solving to what I'm doing here. So if it's a conserved flow in a classical Reynolds solving method, the material here, it would be it can be it will be mostly a solid material. So the fluid wouldn't be actually able to pass through this particular solid here. But in my case, as the fluid can pass through the cartilage, I need to take account of that fluid that's actually going into the cartilage and coming out of the cartilage. In a classical case, if you take the derivative of flow, as the flow is conserved, it would be 0. But in my case, as I have the fluid exchange between cartilage, I need what I say is the derivative of the flow will be equal to the fluid that's exchanged between the cartilage. So this is how I formulate the Reynolds equation, and then I modify the Reynolds equation to take into account the fluid that's exchanged between the cartilage. Now, if I rearrange this particular equation, it would come something like this. This is very similar to the one-dimensional form, but it has the porous term accounted in it. Now, on top of that, you'll be able to see some parameters here, phi in front of all the pressure. This is the wedge term, and then this is the porous flow term. So these are to take into account the roughness of the cartilage. So we have the flow that's passing through a very thin space, but on top of that, cartilage has a small roughness. Now, even if cartilage has a roughness of 1 micrometer, this can significantly affect the flow because we are dealing with a very thin space, and small roughness of the cartilage can also affect the flow. So that's the reason why we have these flow factors implemented in the Reynolds equation to take care of the roughness, so that this roughness helps to alter the pressure accordingly by changing the film thickness and the flow that's going through the thin space. So this is all about the fluid modeling part. And now we need to see how we model the solid cartilage part. Not the solid part, but it's a porous material. So the cartilage here is modeled in FEM. So we have the cartilage modeled in a circular fashion. We have the bone, and then the cartilage is attached to bone. This is a soft material. So the elastic modulus of cartilage is in the range of 10 megapascal. Here you can see how fine the mesh of the cartilage is made. And then these elements can take, these elements are porous elements, which means this can take fluid properties. So when you apply a particular pressure, so this is a kind of typical pressure that we would get after solving the Reynolds equation, the slide that I showed before. So if you apply a pressure like this onto cartilage, this is a typical deformation that you would see. You can see how the model deforms. And then this is the velocity profile plot, which actually says how the fluid would travel along the surface of the cartilage when a particular pressure is applied. Here you can see fluid going into the cartilage in this particular region. And then there's fluid leaving the cartilage at region where there is no pressure being applied. All right. Now, at this stage, we have two different solvers. We have a fluid solver, which we discussed, and then we also have a cartilage model with us. For this problem to work perfectly, we need to couple both these solvers. Now, how this works is we have this solid solver which solve for the deformation and the fluid exchange part of the cartilage. And this information will be used to set up the fluid model. So the deformed profile from the solid solver is used to set up the film thickness for the fluid model, and the fluid model solves for the pressure. So whatever is the flow that can flow through this particular film thickness will be solved, and then this pressure will be applied back to this particular cartilage here, and then this loop keeps on continuing. So for instance, what happens is, so there'll be a deformed model that the cartilage would supply to the fluid model, and then the fluid model will generate a pressure. The fluid model would say to the solid model that, hey, I have a pressure here. Do you think this solid model can withstand this pressure? So the solid model would take that pressure into account and see if it deforms more, or it can maintain the same amount of deformation. So this keeps on iterating until a point when there will be no change in the fluid pressure, as well as there will be no change in the solid pressure. So that's a stage when we call the solution a converged solution, and those are the results we actually look into. To best understand what I said before, this is a small video that explains how this problem works. In this problem, you'll be able to see a circular shape and then a pressure that will be developed. And then the model will keep on running. So I'm just going to play this video here. Oh, yeah. So as you can see, this particular solid model keeps on deforming with the fluid pressure. And this keeps on deforming until a point where the fluid pressure will no longer change, and then the deformation will also stop. So this is a typical converged solution for our problem. Now, as is the modeling work, the first thing that we need to do is to validate our model with the classical models that are already available. So in this one, what we did was we have a model that's built with porosity, and we took this particular porous model. We said that put the permeability of this porous model equals 0, which means there'll be like no exchange of fluid happening within the porous model, which would be very similar to how a solid model would work. A typical solid model would work. Then we had the results of a typical elastohydrodynamic solver solve for the same set of conditions, and then we validated both these results. So as you can see, we were able to get perfect correlations when we had the porous model permeability put to 0. All right, time for a second poll. So this particular activity will help to understand the results much better. So what is your favorite activity to do during the day? Which one do you all prefer most? Walking, jogging, running, or any kind of sports or gym? I'll give you 15 seconds to answer this poll before we move forward. All right, so I see a lot of people answering walking, jogging, running, sports. So we have good mixed kind of response here. All right, so with that, let me move on to the next slide. Next slide. Okay. So the intent of asking the previous question was just to get into your mind about different kind of activities, especially walking, jogging, and running. So with these three particular activities, you see walking is a slow speed activity, so in which your cartilage would move related to each other at a significantly less speed. But when you start jogging and when you start running, that's when the speed of the relative movement of the cartilage keeps on increasing. So that's what we are trying to do here. We are trying to increase the speed of the sliding of the cartilage and trying to see how the pressure varies with the increase in speed. So the interesting results that we see here is as you keep on increasing the speed, which would mean from walking to running, we see more and more pressure being built up in the particular contact area. So what does this rise in pressure mean for us? Before we discuss that, this is how the fluid would exchange between the cartilage. Now, if I separate the regions into three, this I call as the inlet region R1, and we have the region R2, which is the contact region, and then we have the region R3 where the fluid leaves. In the previous slide, we saw almost all the pressure here are developed in this particular contact region. What it means is when there's a pressure developed in this particular region, we see that there's a good amount of fluid that's actually going into the cartilage in this particular contact region. And then there's like a bit of fluid that's being lost at the outlet as well as at the inlet. So this corresponds to a hydrodynamic case in which we still have a small thin film of fluid staying in this particular region, and due to the high pressure that's generated in that fluid in this small thin space, that fluid due to the high amount of pressure is actually going into the cartilage in this particular contact region. Now, as we saw before, as we increase the speed, there's fluid going into the cartilage through this particular contact region. What we also see is if we increase the speed, the sliding speed, we see that there's more and more fluid that's going into the cartilage. Now, the best way to understand this results is usually if you stand for maybe 10-15 minutes, the cartilage would be keep on compressed and the complete fluid in the cartilage would be lost. And after that, if you were to make a short run, your cartilage would absorb all the lost fluid much quicker than walking or jogging. That's the best way to understand these results. Now, we also did a bit of testing on the permeability. So the normal permeability of a cartilage is somewhere around 10⁻⁸. So we did it with an increasing and a lower permeability compared to the normal permeability of cartilage. So what we understand here is when we increase the permeability, there's more fluid that's going into the cartilage. Now, if you don't understand the complete picture, you may get into a confusion that increasing the permeability of a cartilage is a good thing, but that's not actually true. The reason why I say that is because it's not just the fluid that's going into the cartilage, but if you see this particular portion, there's like good amount of fluid that's lost from the cartilage as well. So if you see the net amount of fluid, even if it's a small fluid gain, due to the high permeability of cartilage, it wouldn't be really able to hold that fluid within the cartilage. It would be lost the minute you start loading the cartilage. All right, so that was all about the presentations. A quick summary of what we have done so far. The biggest thing in this particular presentation is about building a fluids solid coupled model. We have successfully able to incorporate surface roughness into the model. We have been able to make this model porous, which means that it can take into account the interstitial fluid within the cartilage, and then we are also able to calculate the flow that's going into the cartilage and fluid that's coming out of the cartilage. Two quick results that we saw, one being the sliding velocity, which actually means if there's like more sliding velocity, there's more rehydration in the cartilage. And then if we increase the permeability, this is more applicable to osteoarthritic patients. So usually if a cartilage is damaged, the permeability of the cartilage increases. And in that particular case, what can happen is the rehydration rate actually decreases, causing the cartilage to quickly compress, and then the bones would directly come into contact, putting them in excruciating pain. All right, so with that, I conclude my presentation. If you have any questions, please do put those in the Q&A section of this webinar. Thank you.
Thank you very much for that, Arshad. That was fantastic. We do have a few questions in the chat for you. The first one is, have you modeled the porosity in the geometry? In that case, have you considered the deformation happening to the porous media, or have you used the value of porosity in the governing equation?
So the porosity of the cartilage is taken care by building this particular FEM model. So what happens is in this particular model, the porosity is a function of deformation. So as and when we keep on compressing the model, there will be like less and less space inside the model, which means there'll be less space for the fluid to stay within the model. So the porosity factor is actually taken into account with the FEM model. Yeah, with the help of void ratios. So we define a void ratio at the beginning, and as we have more deformation coming, the void ratio would change, and then that would affect the porosity, and the fluid within the cartilage would rearrange such that there'll be like less fluid in the cartilage if there's like more deformation. I hope that answers the question.
The next question, we have a question, is frictional wear a phenomenon that can be reproduced for your model?
So that's a very good question. At this particular point, we haven't included the frictional wear capability in the model. But if we want to do that, we'll need to again modify the Reynolds equation to take into account the frictional thing to be incorporated within the model. Yeah, good question.
Thank you for that. And the next question we have is, how do you model the surface roughness?
Great. So the surface roughness is taken care with the help of flow factors. So I haven't put those equations on this particular slide, but this flow factors is a function of surface roughness. I'm using Patio and Cheng surface roughness model to take that into account. So what actually happens is these flow factors will always have a value corresponding to the roughness, and this particular flow factors will modify the wedge term, the pressure term to take that particular surface roughness into account. Thank you. Thank you for the question.
We've got another question for you. If you modeled the asperity deformation, what material properties have you captured for the deformation?
Very interesting question. So at this point, we are not modeling asperities as such. So the cartilage here is a FEM model. The surface roughness which I was talking about is more incorporated into the Reynolds equation of the fluid here, because the surface roughness is more to do with the fluid flow that's actually flowing outside the cartilage. That's the reason why we believe the surface roughness should be like more to do with the fluid that's actually flowing outside the cartilage. And yeah, that's the reason why we did not model asperities in this particular solid model. Yeah, good question. Thank you.
I've got a question for you, if you don't mind, Arshad.
Sure.
So you've talked a lot about, obviously, about those activities of daily living, the running, the walking. In your
Yeah.
model, have you thought about simulating, some of those sit to stand activities that you might see in these patients with osteoarthritis, just the basics?
Oh yeah. So at this particular point, the model is only capable of doing dynamic activities like walking or simulating running cycles. To do stationary activities like standing or sitting, we need to have a slightly different version of this, which I plan to build in the very near future. Yeah, thank you for that question.
And then one more follow-up, if you don't mind. So with your model, you've obviously done, quite a simplified geometry initially at this point in terms of the bone and the loading and the interface surface. Further down the line, have you considered how threading in like a more realistic bone geometry will impact what you're seeing in your model?
Exactly, yeah. So these are the things that I have in my mind to do in the future for this
It's a lot
particular
of work.
project. Yeah. Yeah. So at this particular point, we are more focused to build this complete model and get some realistic results with the experiments. So once we have confidence in this model, and when we do the correlation with the experiments that we already have, that's when we would like try to develop like a 3D model, which would be a very realistic model of a bone and cartilage, and then do some real kind of simulations. Yeah, thank you.
Oh, brilliant. Thank you very much for that talk today. It was very informative. I'm sure everybody who's participating will agree. So, yeah, with that, I'd just like to draw to conclusion the webinar today. If you have any follow-up questions, do get in touch and we can pose them to Arshad. I'm sure he'll be happy to answer those for you. And just a reminder that this is recorded, so if you do want to listen back, please do wait for that to be sent round. Thank you very much, Arshad. Thank you, everyone, for joining us.
Thank you everyone for joining.